So far in our Calculus 2 exploration of integration strategies, we've seen integration by parts, integration by trigonometric identities, and integration by trigonometric substitution. Now, in this video, I've given a particular integral that looks really messy. In this one, we're going to have to tease it out. And I'd actually encourage you to pause the video and to see whether you can come up with an answer to this particular integral yourself. Now, when I look at this, when I try to tease out what could be a strategy, how could I choose an effective strategy? The first thing I like to do is sometimes a bit of a process of elimination. When I think about, could I use a trigonometric identity? I mean, there's lots of trig terms, maybe a trig identity is the thing to do. But if I think about the obvious ones, like for example, Pythagoras, well, in the denominator it doesn't quite work out. There's sort of a weird 4 there. Even if I took that sine to the 4th and expanded it, nothing's going to cancel very nicely. I could take that sine cos term and make it 1/2 of sine 2 theta. That's another identity. But the most obvious identities, none of them really work out. It's also not obviously the case that integration by parts is all that helpful. If I think through a couple different ways I might try to split up this integral, none of them seem to work in terms of setting a u and setting a dv. However, there's one glimmer of hope here, which is that if I think about trigonometric substitution had a whole bunch to do with things where you had like square roots, +1 or -1, and I sort of have that here. I've got this to the power of 3/2. I have this -1. Maybe if I do a bit of massaging first, a bit of substitution first, I can make it an integral where I can use a trigonometric substitution. Now there's a couple choices here. What about u equal to sine of theta? There's certainly a lot of sine of thetas. There'd be a u to the 4th on the bottom, a u on the top. The cosine would become the du. But then I'd still have a u to the 4th on the bottom. It's not quite right for trigonometric substitution. We want like a u squared on the bottom. So what if instead I do this? I will set my u to be equal to twice sine squared of theta. Then my du is going to be 4 times sine of theta, cosine of theta. And if I go and take all of that and plug it in, well, because of the 4 sticking there, you get a 1/4 out the front, and then it's just a du over u squared minus 1 to the power of 3/2. So with a little bit of anticipation, we've chosen a substitution, a u substitution, that puts the integral into a standard form where I can then go and do a trig substitution. Things like u squared minus 1 are screaming to have a trig substitution. Well, which one makes sense if we just focus on this particular integral? Now, you might recall that we have these different Pythagorean identities. There was the sine squared plus cos squared equals 1. You could divide out by cos squared and get tan squared plus 1 is secant squared. Because my integrand here is a u squared minus 1, it's something squared minus 1, I think the bottom of the two integrals makes more sense. Because you could take the 1 to the other side, you get secant squared minus 1, and you can replace that all with tan squared. So let's do secant. That's going to be my trig substitution. U is secant of theta. You, of course, are allowed to go to that chart I've shown before for how to come up with a trigonometric substitution, but I think it's better if you think it through and think through the identity that you're going to use to realize it's going to be best as secant of theta. Nonetheless, given that we've chosen secant of theta, that means our du is going to be secant of theta, tangent of theta, d theta. And then the final thing that we need to figure out is the restriction on the domain. Let's go and plug this in for our substitution. We have this u, we're plugging in secant, and what do we get? The 1/4 of secant tangent d theta on the top, and then secant squared minus 1 to the power of 3/2 on the bottom. Now we can use Pythagoras. We have the tan squared plus 1 is secant squared formula. You rearrange it. Secant squared minus 1 is tan squared. So I can just go and put a tan cubed on the bottom. Tan squared, square rooted is tan, and then cubed is tan cubed. By the way, it was right at this step where we did that business of the restriction of the domain. I had chosen a domain where tangent was always positive, so I could go and put this in and end up with this positive tangent all cubed. Now, there's a tan on the top, there's a tan on the bottom, we can cancel that. That's just going to be secant over tan squared d theta. And now this is a trigonometric integral. We have to use trig identities to try to solve this. Now, at this point in the calculation, I went and paused and tried to do something with this secant over tan squared. Maybe put in a Pythagoras, and nothing was jumping out at me immediately. Working with secants and tans, which do often play nicely together, it wasn't immediately obvious there was a good path forward. So what I'm actually going to do when I focus on this is I've got the secant and the tan and I've color-coded them for you, is I'm going to convert back to sines and cosines. That is, the secant is 1 over cosine, the tangent is sine over cos, but because it's on the bottom, I can flip it so it's cos squared over sine squared. And this is a good strategy. If the secant and tangents aren't obviously working, you could always convert back to sines and cosines. Regardless, now that I've written in terms of sines and cosines, I see there's a canceling of the cosine, and so I can rewrite this as cos over sine squared. Now that we have this in a nice form with sines and cosines, I think I can do a substitution. But I'm going to call it a W substitution because I already did a U substitution earlier on. It's the same sort of idea, but I'm just going to call it W. So I'm going to set W as sine of theta, and of course dW is cosine of theta d theta. And then when I plug that in, I'm going to get the 1/4, the integral of the dW over W squared. This is just the power rule, so we're going to say it's minus 1 over 4W plus the C as it's an indefinite integral. Are we done? Sadly, not quite, because I've done a W substitution, I've done a trig substitution, I've done a U substitution, I've done 3 substitutions, and now I've got it in terms of W. I want to go all the way back to the beginning to get it in terms of X as my original integral was written down in. So I have to undo these 3 different substitutions. The most recent of them was W, so I've got a W here, and I'm going to rewrite it in terms of theta. This is now minus 1/4 sine theta plus C. And that's some progress. I now need to go and undo the trigonometric substitution. That one's a little bit harder. You might remember there's a bit of a rigmarole for dealing with that. In particular, the substitution we had done was that U was secant of theta. That's what my trig substitution was. And I can come up with a little bit of a triangle for that. So if I make a triangle, a right triangle with an angle of theta down here, then what I am saying is that secant of theta, which is the same thing as 1 over cosine of theta. So 1 over cosine of theta is going to be this value of U. So because cosine is going to be the adjacent over the hypotenuse, and I'm doing secant, which is the opposite, then if I make my hypotenuse a U and my adjacent a 1, then indeed secant of theta is just U. And now that I have 2 sides, I can get the third by Pythagoras. I can say that the opposite is the square root of U squared minus 1. And now I can plug it in. What's sine theta? It is going to be the opposite, square root of U squared minus 1, divided by the hypotenuse, which is a U. It's on the bottom, so I flip it, and what do I get? Minus U over 4, the square root of U squared minus 1 plus C. And I am still not done, because even though I've done the trigonometric, if you recall all the way at the back at the beginning, we did an initial U substitution that related U and X. It was U is this twice sine squared of X. I plug that in, what do I get? Minus 2 sine squared of X, all divided by 4 square root of 4 sine to the 4th of X minus 1 plus C. That is a mouthful, but it is indeed our final answer. So my advice to you, when you see sort of a messy integral that doesn't have an obvious step, is just to play around to it. Don't get married to your first choice, your first U substitution or your first strategy. Try to anticipate what might work. The big thing for us here was that I was anticipating a trigonometric substitution. If you don't think about, well, could it be a trig sub? It's very hard to ever get that right answer. So have those in your mind, have that alarm bell going off when you see that square root and that blah to the power of 4th minus 1. Can you make it something squared minus 1 instead? Have those alarm bells going off in your head. Be looking for them. But broadly, just be willing to play around and experiment as you go through your process of trying to solve an integral. Now, if I go back to this chart that we've seen before for how to put in what type of substitution, in that secant case that we're using here, you'll notice that the restriction on the domain is kind of weird. So let me take a brief aside to explain where that restriction on that domain came from. We haven't yet done secant. Well, to do this, I first want to see a graph of secant. Secant is 1 over cosine, so what I'm going to do is graph cosine and secant. In the yellow, I'm going to have cosine. And then for secant, what you do is it's 1 over cosine. So for example, at pi over 2, cosine was 0. So 1 over cosine, which is what secant is, at pi over 2 is going to be a vertical asymptote. Indeed, we get a vertical asymptote. And you can sort of go through the other points and you get this graph. In the pink, this is just going to be our secant of theta. Now, for our restriction on a domain, the consideration we want is some restriction where every value of secant is attained and attained only once. So we want every value, it looks like, from 1 up to infinity and minus infinity up to minus 1. Secant doesn't take any value between minus 1 and 1, that's okay. Now, There's a lot of repetition here because it's periodic, but we want to choose some restriction, and I want to think cleverly about how to do this. If I look at the Pythagorean formula I'm going to use, I'm going to eventually use secant squared minus 1 is tan squared. When I plug it in up here, I'm going to have a square root there because of the power to the 3/2. So I'm going to have a tan squared square rooted, which I want to write as just tangent, but I can only do that if tan is all positive. If tan is sometimes positive and sometimes negative in the region that I restrict to, then I'm going to have to break it up into different cases, some with positive signs, some with negative signs. I don't want to do it. So even though I'm trying to figure out a restriction on the graph of secant, and I put up the graph of secant, let me take a look for a moment at the graph of tangent, which is this. Tangent is periodic, and I notice that it is positive between 0 and pi over 2, and then it is again positive between pi and 3 pi over 2. But it was negative in the middle. It was negative between pi over 2 and pi. So let's keep that in our mind. This is where tangent is positive. So if I now want to make a restriction on the domain of secant, going back to secant, look what I've highlighted in green. The 0 to pi over 2, and the pi to 3 pi over 2. In those regions, in these green regions, tangent would be positive everywhere, so I could do the square root of the square business and just make it equal to positive. I wouldn't be making any mistake. But I have indeed satisfied the conditions of it hits every single value of secant and it hits it only once. So that's how we come up with this particular weird restriction that our thetas are going to be between 0 and pi over 2 and then between pi and 3 pi over 2.